their first paper, in the first paper where they computed a black hole entropy using the Euclidean action, after working out the Schwarzschild solution, they considered the Kerr solution, which describes a rotating black hole. And upon continuation to imaginary time, the Kerr solution becomes complex. They called it a quasi-Euclidean spacetime. But it was smooth. It had a complex metric, but otherwise everything was fine. They computed its action, and from its action, they were able to get sensible results for the thermodynamics of a rotating black hole. So that was at least one case in which it appeared appropriate to consider complex solutions of the Einstein equations, namely the quasi-Euclidean version of the Kerr solution. So numerous other possible reasons to look at complex space-time metrics have been considered more recently. So one which will be important later in my lecture involves topology change. So Luko and Sorkin in 1995 considered topology change. For example, well, they weren't motivated by string theory, but in string theory, you would say they were doing string perturbation theory, one string breaking into two, which we usually discuss with the Euclidean signature worldsheet, but they decided to study it with the Lorentz signature worldsheet. Now, you can easily, so think of time as running vertically. The time function has a critical point at the saddle points of the metric. So it's easy to write a Lorentz signature metric on this space, which is smooth and fine everywhere, except that it becomes degenerate at the critical point. The only thing wrong with it is that there's one point at which the metric is not invertible. In fact, it's zero. But otherwise, it's smooth and it has Lorentz signature except at one bad point. So there can't be a good Lorentz signature metric because informally, the time would have a stagnation point, and you can make that rigorous. But they slightly regularize the situation by letting the metric become complex near the critical points. And doing that, they got what looked like sensible results. So it seemed like what they say is what you have to do if you want to do string perturbation theory with Lorentz signature, spacetime, and worldsheets. Although, again, they weren't motivated by string theory, so they didn't say it that way. Another motivation for complex metrics has to do with the Hartle-Hawking wave function of the universe. So if we're doing quantum gravity in d dimensions, let Y be a d-1 manifold with metric g sub d-1. So the Hartle-Hawking wave function is supposed to be a function that depends on a d-1 metric gd-1. And you're supposed to compute it by summing over all d manifolds M whose boundary is Y. And for each M, you do a path integral over all metrics on M whose boundary value is d-1. So here's a picture. We specified Y including its metric, and then we allow all possible M's with all possible metrics on M. And doing a gravitational path integral over all that stuff, we get what's supposed to be the Hartle-Hawking wave function. So this is what you do for an ordinary quantum field rather than gravity, but with one important difference. For an ordinary quantum field, you would indeed specify the boundary values on Y, but you'd pick an M, and you'd also pick a metric on M. And then you'd compute a wave function of this kind for a particular M. So adapting it to gravity, Hartle and Hawking just said that in gravity, you sum and integrate over all possible M's and all possible metrics on M. So for usual quantum fields, to find ground states, one uses Euclidean path integrals, and Hartle and Hawking wanted to find a natural state, which would be in some sense an analog of a ground state. So they said you should do it by a Euclidean path integral on M, summed over M. Incidentally, the sense in which this was supposed to be a ground state was not well defined. They just said they wanted to imitate what you do usually to get a ground state, to get something that would be a gravitational analog of a ground state. It wasn't stated more precisely than that. Now, immediately, if you try to do this, a few things are strange. Well, first of all, if the Einstein-Hilbert action were bounded below, it would behave in a way more similar to what we're familiar with. If there were a lower bound on the Einstein-Hilbert action, then the exponential of minus the lower bound would be the asymptotic behavior of this wave function in a semi-classical limit where Y is big. So if there were a lower bound, because of the way the Einstein action scales with the volume, it would grow when you scale up the volume of y. And if y is big, the action would be big, and the integral would be dominated by the smallest value the action could have. And so assuming the greatest lower bound is positive, which would happen if the Einstein and Hilbert action had the positivity of normal quantum field theory actions, you get exponential decay for large volumes. So that's what happens for ordinary quantum fields. For example, if phi is a scalar field with a positive definite action, like a free field action, the corresponding wave function decays exponentially. In fact, it decays like a Gaussian for large phi, because the action, the minimum possible action, grows quadratically with phi. Well, this is the answer for a normal quantum field, but we don't want to get that answer for gravity, because then we predict that it's extremely unlikely to observe a large universe. So something else has to happen if we don't want to predict that we're not going to see a large universe. But what saves us is that actually the Einstein-Hilbert action is unbounded below. So there's no lower bound on the action of a metric that satisfies the boundary condition. And therefore, we don't predict that it's exponentially unlikely to observe a large universe. But since that's the case, what does the gravitational path integral mean? Well, Gibbons, Hawking, and Perry suggested that it's a middle dimensional contour integral in the space of complex valued metrics. But what's the contour?
Edward?
Yeah.
Can I ask a question about this large universe issue? I agree with the math, but I feel that the issue with the problem that they had was actually that they predicted a universe that would start large. Right? There would have been nothing wrong with predicting a universe that starts small and then has a long period of inflation.
Sorry, Raphael, you're jumping ahead. You should criticize a later remark. But right now, there's nothing for you to criticize. Had the Einstein-Hilbert action been bounded below, we simply would have said that it was exponentially unlikely in this wave function to have a large universe. So for that objection, there will be a fix, but you should postpone your objection a little bit later until I explain the fix.
Well, your statement seems to, maybe I'm misunderstanding, but it seems to conflate producing an initially large universe with having a large universe that we can observe today.
Well, there's no initial and no final. There's no evolution. This is simply supposed to be the universe as a function of spatial metrics. So when you observe today, you're supposed to be observing this GD minus 1.
Well, you could have a universe that evolves to a large universe in Lorentzian time, which has very small Euclidean action.
Evolve doesn't mean anything here. There simply was a recipe to calculate a wave function. Literally, what you're saying doesn't make any sense. We'll get to something that's more like what you're saying in a moment, but you're asking your question prematurely. Literally, had the Einstein-Hilbert action been positive definite, this wave function, computed this way, was supposed to be simply the wave function we observe. But ask your question again, I think, in a little while. So what saves us is that the Einstein-Hilbert action is unbounded below, so that you can't make that kind of argument. But given this, what does the gravitational path integral mean? Well, it was suggested it was some kind of middle dimensional contour integral, but to this day, there's no serious proposal about what the contour would be. One can't say anything better than what Gibbons, Hawking, and Perry said, which, to use a fancier language than they used, is that the contour integral, the contour would be a sum of Lefschetz thimbles associated to critical points. They just said that you would take critical points or classical solutions. For each critical point, you would do a semi-classical path integral, and then you have to think of something better in higher approximations. But a fancier way to say that is that the contours would be Lefschetz thimbles associated to critical points. But anyway, semi-classically, we sum over classical solutions with no clear guidance on what to pick. For each solution, we evaluate its contribution perturbatively. So to try to actually compute the Hartle-Hawking wave function in examples, we need to pick some classical solutions. Here again, we run into what looks like an obstacle, but perhaps it's really a benefit. In simple cases, there appear to be no real Euclidean signature solutions, although as far as I know, there's no proof of this statement. For instance, consider Einstein's theory with a positive cosmological constant. I've written it in Euclidean signature, and with the signs being such that the cosmological constant is positive. And take the d minus 1 manifold Y to be a sphere SD minus 1 with a round metric of large radius. Large means large compared to the length scale set by the cosmological constant. Well, it's believed that in this problem where you specify Y and look for a metric on M that satisfies the Einstein equations, there's no real solution, no real Euclidean classical solution. It would be nice to prove that. As far as I know, it's unproved. However, if we broaden our horizons a little and all the complex solutions of the Einstein equations, then there is one that gives a somewhat sensible answer, although vulnerable to Raphael's criticism. So to explain how to make complex solutions, we start with the metric of a D sphere, which I've written here. Rho is a constant, the radius of curvature. And d omega squared is the metric on a d minus 1 sphere. And now to make complex solutions, we could complexify this spacetime and take a real slice in it. But for simplicity, I'll leave the d minus 1 sphere real and just complexify theta. So we get a sphere if theta runs on the real axis from minus pi over 2 to pi over 2. But there are a lot of other things we can make by considering a curve theta of u in the complex theta plane, where u is a real variable. So I've drawn the theta plane showing some of the zeros of the function cosine theta. The reason the zeros are important is that if the curve theta of u is going to have an endpoint, the endpoint has to be one of the zeros, or else we'll get a manifold with boundary. So, well, we might want a manifold with boundary because we do want one boundary in this problem. But if we only want one boundary, the other endpoint has to be a 0. And if we don't want any boundaries, then both endpoints have to be zeros, or else we could take a closed curve in the theta plane with no zeros. So we can do lots of funny things with different curves. So, well, first of all, here are two real solutions. A straight line from minus pi over 2 to pi over 2 gives a sphere, as I told you already. And a straight line that runs on the whole imaginary axis from minus I infinity to I infinity gives de Sitter space with this metric. So theta is IU, U now becomes real time. These are both considered physically sensible solutions. Here's another solution that's also considered important. So here the way it's usually described, okay, you take a hemisphere. So you take half of this one and half of this one. So half of this one is a hemisphere rather than a sphere, and half of this one is the future evolution of de Sitter space. So this solution describes a hemisphere that's glued onto half of de Sitter space. The way people usually describe it is that you integrate over a hemisphere to prepare a state, and then you let the state evolve in real time on the red part of the contour. So it's viewed as describing creation from nothing of a closed universe that then expands exponentially fast. Here's a smoother version of the same picture. So we simply take a curve in the complex theta plane that starts at pi over 2 and goes to I infinity. After a little while, it hugs the real axis. You can make it run exactly on the real axis after a finite time. So this way you can make a smooth complex metric that is in de Sitter space in the future. Now, it's Lorentzian in the future, but you see, it solves our problem because the boundary values along Y are completely real. So the metric isn't real on M, but the boundary values on Y are completely real. So if you pose the problem of finding a solution of Einstein's equations, where the boundary is a sphere of very large radius compared to the cosmological constant, then there's a smooth complex saddle point that solves that problem, which is given by this kind of curve. If you prefer, you can make a non-smooth one, which is piecewise Euclidean or Lorentzian, or if you like it better, you can make a smooth one. But either way, on the boundary, the metric is completely real. So it's believed that for a positive cosmological constant with a sphere that's too big, there's no real saddle point in the Einstein equations, but there is this complex saddle point. Because it's complex, the action has both a real part and an imaginary part. the real part is actually minus half the Gibbons-Hawking de Sitter entropy. And then there's an imaginary part that grows with real time. So the semi-classical answer looks something like this. And it's a somewhat sensible answer, a more or less physically sensible answer, where the real part means that there was a large probability to produce this because somehow the Gibbons-Hawking entropy means there were many microstates. And the imaginary part describes, it has an oscillatory behavior, so it describes real-time evolution as a function of the volume. However, once we start to, so this is where Raphael should have objected, in my opinion, but maybe I didn't claim too much to make him object. However, once we start allowing complex metrics, we're opening Pandora's box. We could do a lot of other things that will not give physically sensible results. For example, here's another complex metric on SD with an action different from the standard value. And instead of going from minus 3 pi over 2 to 3 pi over 2, I could have connected any two zeros of the cosine theta, of cosine theta. Or I could have taken a closed loop in the theta plane, and that would have given us a complex classical solution whose topology is S1 times SD minus 1. And after a little thought, you'll see its action is 0. You probably don't want a zero action saddle point of the Einstein equations. And here's a complex solution, which, if we allow it, gives a contribution to creation of a universe from nothing with an even more negative real part of the action. That's actually true in, I think, odd space-time dimensions. And we could make it worse by starting at 5 pi over 2.
Do you expect the complex saddles to appear in some pairs, like the complex contribution will cancel, or not really?
Well, they don't try to cancel because naively the complex conjugate guy has a complex conjugate contribution to the action. But moreover, we don't want to let them cancel because, okay. What people usually say is that this one describes an expanding universe and the other one describes the time reverse of an expanding universe, a contracting universe that disappears, or something like that.
I see.
Anyway, there's no suggestion along the lines of what you said. But
Why,
anyway,
why would we not want the zero action solutions? Because
Well,
those
let me
can play a
tell you,
role in the overall renormalization.
well, let me tell you a worse zero action solution. I decided in preparing the talk not to prepare slides to explain it in detail, but you know about gravitational wormholes that connect two different universes. You can easily construct a zero action complex wormhole that connects two asymptotically flat worlds. So you can have two copies of RD with a smooth solution of the Einstein equations, whose topology is a wormhole. The action is 0, but the metric is complex. And you don't have to connect two different worlds. You can connect a world to itself. So it has the same action as flat RD, namely 0. So if you decided to include it, you would certainly get pathological results because it would compete with empty flat space. But I've mentioned a lot of things that would give pathological results. Maybe the standard creation of the universe from nothing, where you start at pi over 2, is physically sensible, but the other guys with the more negative action are certainly not. So we need to, yeah.
Just briefly on this issue of whether one should include two saddle points or one. If you specify the metric as the argument of the wave function, it doesn't distinguish between expanding and contracting universes. If you specify the extrinsic curvature, it would.
Yeah, that's true. So that question, and that's a mathematically better question. I even wrote a paper about it. Specifying the boundary metric is actually not a well-defined mathematical problem. It's not elliptic. Specifying the extrinsic curvature is elliptic. So it's a better defined wave function. And so, well, there's a long history of people suggesting that might be a better thing to do for different reasons. Well, although I was just summarizing standard facts from the math literature, I did write a small paper pointing out what I just told you, that it was simply a mathematically better defined problem. What I mean by that is that if you specify K and find a classical solution, perturbation theory around it will be well defined. That's, I believe, in general, not true if you've specified the boundary metric. But the general story is tricky. So anyway, well, I gave a couple examples, but well, I didn't explain in detail the wormhole, which I think is a nice example. But anyway, there are lots of examples of complex saddle points that would give us unphysical results if we include them. So we need a principle that would help us select what complex solutions we think are sensible. So in a recent paper, Kontsevich and Siegel made a suggestion for a distinguished class of allowable complex metrics, which were supposed to have the property that ordinary quantum field theory makes sense when coupled to allowable metrics. So their motivation was not quantum gravity. They were trying to develop an alternative to some of the standard axioms of quantum field theory. The new axiom set would assert that quantum field theory can be consistently coupled on allowable metrics. And they have some results in their paper, so not a complete story, showing that some standard properties can be recovered from this starting point. And well, some can be understood in a more illuminating way. So personally, I hope it turns out to be a good axiom set, but that's certainly not known right now. Although their motivation wasn't quantum gravity, we could observe, and many previous authors have observed, among others, Allowable and Hartle and Luco and Sorko, and probably others I don't know about, pointed out that whatever saddle point you allow, if there's matter coupled to quantum gravity, you want to do perturbation theory, and you hope that the quantum matter system makes sense in the background metric you've assumed. So complex metrics in which quantum field theory doesn't make sense are a good class. And that's what they were trying to propose with a different motivation. So my only observation in this talk is a rather simple one, which is that the good complex metrics that seem to have given useful results, in the example I described and some other examples I won't really talk about today, seem to be allowable. And the obvious bad ones, including the bad ones I've mentioned, and some similar ones like the wormhole, are not allowable. So at least, maybe this is too optimistic, but at least in a lot of simple examples, the allowable criterion removes bad critical points and allows good ones. I should add that Luco and Sorkin and their work on topology change had a notion of good complex metrics, mostly in dimension 2, and not developed this systematically. But as far as they went, it was similar to the notion of Kontsevich and Siegel. The idea of Kontsevich and Siegel was to require that the theory of a P-form field A makes sense for every P from 0 up to D minus 1. So if I let F equals dA be the curvature of the P-form and write Q equals P plus 1, the usual action is this one. And then the requirement is that a metric is allowable, is that the real part of IQ should be positive for every real non-zero F and all Q. The intuitive idea is that positivity of the real part of the action implies that the path integral of an anti-symmetric tensor field coupled to the metric G makes sense. So in other words, their condition is that the real part of the action of an anti-symmetric tensor field is positive. So the path integral of the anti-symmetric tensor field makes sense. Since the positivity of the real part is supposed to hold for arbitrary real F, it's really a pointwise condition on M. At each point, the quadratic form that appears in the action has positive real part. And that's supposed to be true for all Q. You might be a little skeptical of attaching so much weight to anti-symmetric tensor fields. In fact, in their paper, Kontsevich and Siegel were rather diffident on this point. Why not symmetric tensors, for instance? Well, there's a nice fact that according to the D-dimensional version of a result by Weinberg and me, which had some help from Sidney Coleman, the only massless fields that have local energy momentum tensors and therefore can potentially be defined in curved spacetime are the anti-symmetric tensors. And their nonlinear versions when P is 0 or 1, which are nonlinear sigma models on non-Abelian gauge fields. But the Kontsevich-Siegel condition isn't changed if you include these nonlinear versions of P-forms. So in other words, basically the theories considered by Kontsevich and Siegel are all the known quantum field theories that can be derived from underlying classical field theories.
Does asking that the dilaton have a well-defined kinetic term pose any additional constraint or not?
Well, in Einstein frame, the dilaton is just an ordinary scalar field. So it's the p equals 0 case of this. So we should make, well, we could discuss whether we should do it in string frame, but at least in Einstein frame, that would answer your question. So it's well motivated to consider, well, for the application of Kontsevich and Siegel, this is definitely well motivated. This criterion covers all known quantum field theories that have classical limits. And although we do know quantum field theories that don't seem to have classical limits, we don't know them well enough to formulate a criterion for them. So their criterion seems right for all the theories we actually know. So in that sense, it seems like a well-motivated criterion for their application, which is to study ordinary flat space quantum field theory. It's a little bit less clear in quantum gravity, but I think it's a reasonable criterion to try. Now, they gave a rather explicit description of the allowable metrics. The criterion is as follows: if G is allowable, then there's a real basis of the tangent space at any point in which the metric is diagonal. In general, with complex eigenvalues lambda I, which are all non-zero, because otherwise the metric is degenerate. The metric is required to be invertible. But then they show that, see, a general complex metric can't be diagonalized in a real basis. They showed that allowable ones can be diagonalized in a real basis. And when you do that, the sum of arg lambda I is less than pi. And conversely, such a metric is allowable. These are precisely the allowable metrics. The proof goes as follows. First of all, the Q equals 1 case of the condition of allowability says that the square root of G times G inverse has positive real part. Now let's write this metric as A plus IB. It follows that A and B can be simultaneously diagonalized by a real linear transformation. You first diagonalize A. See, you're given that A has positive real part, so it can be diagonalized by a real linear transformation. And that's only unique up to SOD. And use the residual SOD to also diagonalize B, since B is a symmetric tensor. Every symmetric tensor can be diagonalized by SOD. So after diagonalizing A and B, this thing is diagonal. So there's a real basis that made root G times G inverse diagonal, and in the same basis, the inverse matrix is diagonal, but multiplying by a scalar, namely the square root of G, I assume you realize, means the square root of the determinant of G. Multiplying by that scalar doesn't affect the fact that the matrix is diagonal. So we learned that there's a real basis of the tangent space in which G is diagonal. Now, once we know that there is a real basis of the tangent space in which G is diagonal, it's easy to implement the condition that the quadratic form is always positive. Sorry, except I miswrote this badly. Sorry. So this is meant to be F times F, where one F has indices I1 up to IQ, and the other has indices J1 up to JQ. I can't account for this mess that I've written here. But remember, this funny thing times F is meant to be the action of a field with a Q-form field strength. And then we consider the case that F has only one non-zero component, which corresponds to the indices being a subset S of the set from 1 to Q. And positivity, for that, the case that F has that one real component, gives the condition that this is positive. And since we had the choice of picking Q, and we also could pick which matrix element of Q was non-zero in this basis where G took this form, we learned that this expression is positive for every finite subset S of the set from 1 to Q. And a little thought will show that the condition for this to be true for all S is this one. So concretely, that's the condition for a metric to be allowable. So a corollary, as Kontsevich and Siegel note, is that the space of allowable metrics is contractible onto the space of Euclidean metrics. You see, after writing Gij equals lambda I times delta Ij, none of the lambdas are negative because a single negative lambda would violate this. Arg lambda would be pi, and that would the sum has to be strictly less than pi. Since none of the lambdas are negative, you can, in a unique way, rotate them in the complex plane to make them positive. If lambda has positive imaginary part, you rotate it in the upper half plane. If it has negative imaginary part, rotate it in the lower half plane. So you can contract the space of allowable metrics onto the space of Euclidean ones. So for example, in 2 dimensions, the Gauss-Bonnet integral, well, first of all, it can be defined for any non-degenerate complex metric. And Luko and Sorkin noted that in general, it does not have its usual value. But for an allowable complex metric, it has its usual value because allowable ones can be deformed onto Euclidean ones, while remaining in the space of non-degenerate metrics where the Gauss-Bonnet integral is a topological invariant. So in that sense, allowable metrics are less exotic than non-allowable complex metrics. If G is allowable, the volume of M has positive real parts, since that's the Q equals 0 case of allowability. But Kontsevich and Siegel proved that if M has an allowable metric, then the induced metric on any submanifold N of M is also allowable. And therefore, every N has a volume of positive real part. We can take that as an indication that perturbative string theory and brane theory are well defined on such an M. So the input was that P forms are well defined on M, but the output strongly suggests that string theory and everything that comes with string theory is well defined on M. This is a little bit heuristic, but it's highly suggestive, I think. Now, the condition for allowability shows that a Lorentz signature metric is not quite allowable because it has a single lambda that's negative, the others being positive. It's on the border of the space of allowable metrics. It can be perturbed in either of 2 ways to make it allowable. We add a plus or minus I epsilon to the coefficient of dt squared. And those metrics are allowable. So we could have considered a more general perturbation. This is a special case. But this gives 2 ways to approach a Lorentz signature metric from within the space of allowable metrics. So in 2 different ways, Lorentz signature metrics are on the boundary of the allowed space. The 2 choices differ by the sign of the square root of the determinant of G. For an allowable metric, the square root of the determinant of G has positive real part by definition. But when you approach Lorentz signature by taking epsilon to 0, the square root of the determinant of G becomes imaginary. The determinant of G becomes negative, so its square root becomes imaginary. But the square root of the determinant of G approaches the positive or negative imaginary axis, depending on the sign of the I epsilon. So you see, that means that the sign of the Lorentz signature action depends on which way we approach allowability. With one way, we'll get the standard sign of our Lorentz signature action. With the other way, we'll get the opposite sign. The sign of the Lorentz signature action is actually a convention. There was no I in classical mechanics, but when Feynman told you to use e to the is, where s was the classical action, in quantum mechanics, he arbitrarily picked I rather than minus I. Well, he was matching other conventions. There was an I in the Schrodinger equation. The Schrodinger equation could have been minus I d psi dt equals h psi, but Schrodinger wrote it with a plus I, or maybe Heisenberg did. Anyway, the founders of quantum mechanics put an I in the Schrodinger equation and made a choice. So one regulator here will give the standard choice, the other gives the opposite choice. The other will give a complex conjugate Lorentz signature path integral with the opposite integrand. In the Schwinger-Keldysh approach to thermal physics, the path integral with one of them propagates the ket and the other one propagates the bra, which depends on a convention, as I've said. Either way, the epsilon in this formalism plays a similar role to the usual Feynman I epsilon. A Lorentz signature evolution is always accompanied by a little bit of Euclidean evolution as a regulator. Clearly, we can't go continuously from positive epsilon to negative epsilon. That helps in understanding what's wrong with some of the oddball metrics I described before. So some of them violated the condition. Well, they all violate the condition that the sum of the arguments is less than pi. So, well, one necessary criterion is that an allowable metric can't cross one of the lines where a real part of theta is 0, because on such a line, cosine squared theta is negative. And crossing such a line is like going from positive to negative epsilon. So that criterion rules out this guy. The same rules out this one. And there are lots of other, well, for example, you could take a closed loop in the theta plane. Well, it can avoid crossing one of the illegal lines, but real theta will have a maximum and a minimum. And if you look more carefully, you'll see that if real theta has a maximum or a minimum, but also gives a non-allowable metric. So the metrics that we do want. So the one that started at pi over 2 and goes to I infinity is allowable. The bad ones are not allowable. And the same is true for a lot of undesirable metrics that I didn't describe in detail at the beginning part of my talk. They turn out to be unallowable.
Sorry, just a quick question. Wouldn't this problem of going continuously between IS and minus IS be solved if we looked at, instead of the metric itself, we looked at like a field bind for the metric?
Well, we don't want to be able to go continuously from e to the IS to e to the minus IS. They give complex conjugate amplitudes. So the fact that the two different regularizations of the Lorentz signature metric are not close by is a feature, not a bug. We don't want to get rid of that. This was the right answer.
Okay, but it doesn't prevent us from switching mid-path integral from one to the other.
Depends what you mean by switching. But you can continuously connect them in different ways, but they're not close by. You can't connect them by changing from positive epsilon to negative epsilon. What we got here was a physically sensible answer, that e to the IS and e to the minus IS were fundamentally different. They're not close by in any reasonable sense. So I gave you a few examples of complex idle points we don't want, and others like the wormhole that I didn't describe in detail, and they're all unallowable. So on the other hand, the allowable metrics, the complex metrics from which useful results have come turn out to be allowable. So one of the more interesting examples, well, there are various examples of this, but one of the more interesting examples is that the quasi-Euclidean metric of Gibbons and Hawking that I started with turns out to be allowable when and only when the black hole is such that one would expect quantum corrections to be well defined. So this is a little subtle. The thermodynamics of a Schwarzschild black hole is related to a standard thermal ensemble, trace e to the minus beta h, where h is bounded below, and that's a good ensemble. The thermodynamics of a rotating Kerr black hole is related to a more general ensemble, trace of e to the minus beta times h minus omega j, where j is a conserved angular momentum and omega is called the angular velocity. But in an asymptotically flat spacetime, this ensemble is unstable because a particle far from the black hole can have a negative value of h minus omega j. So you can do the classical calculations that Gibbons and Hawking did. Yes, that Gibbons and Hawking did. But if you try to calculate quantum corrections, you can't expect to get a sensible result. The quantum corrections aren't well defined, and it turns out this is reflected in the fact that in an asymptotically flat spacetime, the quasi-Euclidean metric is not allowable. It's not a metric where you can do quantum corrections, and you shouldn't be able to because the ensemble wasn't well behaved. However, it was noted in the early days of the ADS-CFT correspondence that the situation is better in anti-de Sitter space. A black hole that's rotating not too fast, in other words, omega is sufficiently small, has the property that h minus omega j is bounded below. So this is most obvious perhaps in the boundary CFT. In CFT, or if you formulate CFT on a unit sphere, the energy is bounded below by the angular momentum times 1. So in CFT units on the unit sphere, if omega is less than 1, then h minus omega j is bounded below. So this is the case that you can hope that quantum corrections will make sense. So in this situation, this is the case where we should hope that the metric is allowable. It turns out that precisely when h minus omega j is bounded below, the quasi-Euclidean metric is allowable. So Hawking and Real showed that in anti-de Sitter space, there are metrics where omega is too big. So these metrics are not dual to anything reasonable on the boundary. They have the property that h minus omega j is not bounded below from a bulk point of view. So in that case, the quasi-Euclidean metric won't be allowable. But in the cases where h minus omega j is bounded below, the quasi-Euclidean metric is allowable. In Lorentz signature, the condition for h minus omega j to be bounded below for excitations outside the horizon is that the killing vector field V that generates this conserved charge is everywhere time-like outside the horizon. Thus, when and only when V is everywhere time-like outside the horizon, you can hope for the quasi-Euclidean metric to be allowable. So with this in mind, let's look at a rotating black hole in 4 dimensions. We could do other dimensions, but 4 is illustrative. So here's the general form of the metric of a rotating black hole, where rotations and time translations shift phi and t. And the various functions written here depend only on r and theta, not phi and t. The horizon is the outermost surface where n squared is 0. Part of the definition of asymptotically flat or asymptotically anti-de Sitter is that n goes to 0 at infinity. An important fact in constructing the quasi-Euclidean solution is that n phi is a constant on the horizon. In fact, that constant is none other than the angular velocity that appears in the thermodynamics. So to construct the quasi-Euclidean metric, it's convenient to introduce a new angular coordinate, phi tilde, which is phi minus omega t. So this one was chosen to make n phi 0 at infinity. So this one was natural to an observer at infinity. Near the horizon, this one is more natural. The metric then looks like this. So but for our purposes, I've made this change of coordinates because the construction of the quasi-Euclidean metric is then more obvious. So first of all, the vector field that generates h minus omega j is just d by dt with fixed phi tilde. And the condition for it to be everywhere time-like outside the horizon is that GTT is positive in this coordinate system. Not in this one, where it isn't true, because there's an ergosphere, but in this one, GTT has a contribution from this term. Although n squared becomes negative. Sorry, I'm saying something wrong, but anyway, a true statement is that GTT is positive outside the horizon. I mistakenly said that the horizon was the outermost 0 of n squared. The horizon is the outermost 0 of GTT in this coordinate system. So in these coordinates, the quasi-Euclidean metric is just gotten by discarding the region behind the horizon, forgetting the value of phi tilde on the horizon, and replacing t by I tau. So this is the quasi-Euclidean metric. And from the criterion for allowability, it's fairly obvious that r and theta have nothing to do with it. We can just look at this part of the metric. So we just need to know if this 2-dimensional metric is allowable. So we reduce to understanding the allowability of a 2-dimensional metric where A and C are real and B is imaginary. Sorry. There should be an I here. This should be 2 pi times IB, d tau d phi tilde. So I'm just using the fact that the only imaginary part was the d tau d phi part of the metric. The d tau squared and d phi squared parts were both real. So A and C are real and B needs an I. It turns out that such a metric is allowable if and only if A and C are positive. So necessity of that follows immediately from the fact that the square root of G times G inverse. This should be G inverse, not G minus J. Remember, what we previously used the fact that this is a special case of allowability, that root G times G inverse has a positive real part. That implies that A and C should be positive. And once you know that, you can put this metric in the diagonal form, and you find that another misprint here, the argument of lambda1 and the argument of lambda2 are equal and less than pi over 2. So their sum is less than pi. So a lot of misprints on the last couple of pages, which I'm afraid were written hastily last night. But anyway, you can saturate the condition that the argument of lambda1 plus the argument of lambda2 in absolute value can be close to, but no bigger than pi, but you can't violate that condition. So in the application to the black hole, C is always positive, A is positive outside the horizon, if and only if we expect the ensemble we're citing to be well-defined. So in other words, precisely when we expect quantum corrections to the black hole will make sense, the quasi-Euclidean metric is allowable. In short, I've explained why it's motivated to consider complex solutions of Einstein's equations in the context of quantum gravity, why a good class of complex metrics is needed, and why the class identified by Kontsevich and Siegel has at least some of the right properties. Thank you. Oh, well, there's a lot. The thank you was slightly premature, so I added a couple of remarks. There's a lot missing. Perhaps most importantly, to get a sensible story, you'd want to have much more than a good class of complex metrics. Ideally, you'd have an integration cycle in the good class of complex metrics, but it's extremely unclear whether or why that would exist. Now I'll stop and say thank you.
Thank Edward. Okay, questions?
Yes, Rahel.
Do you have any comments on Euclidean wormholes that recently have, I guess, become a topic of great interest? And this would support that we should include them, right?
I think it's relatively clear that we have to include general topologies, but we don't want to. But we don't want to include complex wormholes with zero action. That would be unphysical. So I didn't quite explain how to construct them, but they're easily constructed, and they're not the examples I know are not allowable. Let me say that there's okay. When they started worrying about such things, I think it was originally Gibbons, Hawking, and Perry who formulated a positive action conjecture on general relativity. So the Euclidean action is not positive, but well, they conjectured that for all metrics of non-negative scalar curvature, the action was positive. That was proved by Schern and Yale, actually. The special case of it is the conjecture that there are no classical solutions asymptotic to R4 except R4 itself. It's a special case because you can easily prove that the action of such a solution would be zero. So the absence of such solutions is a special case of the positive action solution. I would like to prove that there are no complex allowable solutions that are asymptotic to R4 other than R4 itself. I don't know how to prove it. It's definitely not true without the allowability. But to answer your question again, I don't have anything novel to say about Euclidean wormholes from this point of view. Some of the examples.
Somebody else is asking questions. I'll ask another one. This is, I guess, related to your last sentence on the slide. I mean, yes. We've always, I suppose, been working under the assumption that the gravity path integral isn't a well-defined thing, and that when we consider these saddle points, it's not clear what we're computing an approximation to. Mm-hmm. But this kind of progress could make you perhaps optimistic that this could be a step towards making it well-defined. Is that something that, are there any concrete directions that you see from here that where you would exploit those results to get some constraints on how it should be defined?
Well, to me, the way it should be defined is by the multi-dimensional generalization of steepest descent, which means you start at a critical point and you solve certain flow equations that tell you to flow downward to make the real part of the action, well, more positive. So the exponential of minus the action is smaller. The only trouble is that for gravity, that equation isn't very nice. So
in settings where there is no critical point, would you then argue that the path integral just vanishes?
I think there's always, it's extremely important, and philosophically, we're discussing Morse theory. And in Morse theory, you have to allow critical points at infinity. What people have called settings with no critical points, I think should be understood as settings with critical points at infinity. Let me give you an example. If I can manage to write on my slides, that would help. I resisted trying to do it before. So there was this story by Stodds, Schenker, and Stanford. So they were doing Jacob, tidal and gravity. And so then they computed wormhole contributions to the path integral of asymptotically ADS2 space. And there's no true critical points, but there is a very nice critical point at infinity. You see, what they said was that they had a parameter B, which was the circumference of this cycle that I haven't quite drawn. And there was a tension forcing it to 0. And in fact, you should consider the case that it is 0. Then you get a perfectly good solution, except it has 2 components. One is ADS2, and the other is a Riemann surface with a puncture, and they're glued together at a point.
So we would not lose this setting because of the fact that you can expand around that.
No, let me give you one more example. The most famous, perhaps real-world instanton calculation was by 't Hooft, calculating proton decay in the standard model, or one of the most famous. That was a setting where there was no true critical points. There was instantons coupled to Higgs fields. So there was a tension that tends to make the instanton shrink to a point. So one might well suspect that this is at infinity in gravity, but in a better theory, it would not be at infinity. That might be a perfectly normal critical point. That would be what I would think. Let me give it just as further motivation for that remark. In Yang-Mills theory, the point instanton is singular, but in string theory, it's not. So that's an example of embedding a theory in a better theory, where what seemed like a critical point at infinity in 't Hooft's calculation does not have that interpretation in a more complete theory. So I would think this kind of situation doesn't involve question, doesn't really, well, technically it's a nuisance that the critical point is at infinity.
So there's actually a question in the chat, and the question is, what does the issue with quantum corrections suggest for de Sitter extensions of holography?
I don't have anything very smart to say. The metric that created de Sitter space from nothing is allowable. So very likely, if you have your favorite quantum field theory like QCD or something, it makes sense coupled to that metric. That's certainly an extrapolation from what's known, but I'd consider it plausible. So the only issue here is whether the quantum corrections make sense. We don't get anything from allowability, at least at this level of discussion, except claiming that the corrections make sense.
Well, so do you believe that, so from what, if I understood correctly, this allowableness condition requires that we kill off some of the cycles in the path integral that would appear from Lifshitz symbols that arise from this unallowable critical points, right? Do you think that there will be some deeper reason of why we do that, that is not just restricting the path integral in this way?
Well, we can't include the ones where the quantum corrections don't make sense.
Right.
I mean, that's been said before. I don't know who said it first, but it was certainly said by Hartle and Hartle 30 years ago, roughly. More than 30 years ago. what I've told you is an attempt to make more concrete what are the kinds of metrics where the quantum corrections do make sense. And I think it's a plausible proposal. There might be stronger criteria than allowability. My only comment in answer to Raphael, unfortunately, you see, it would take some time to explain what I mean by how you should try to construct an integration cycle. But the general notion that generalizes stationary phase for one-dimensional integrals. People talk of steepest descent, but people often describe steepest descent in a way that only makes sense in one dimension where it reduces stationary phase. In general, steepest descent tells you to introduce another time variable, which is not one of the space-time coordinates, and then try to let the fields evolve according to this equation. dg dt is minus di dg bar, where G is meant to be a completely general field. It wasn't necessarily meant to be the metric there. And also I should discuss how you deal with gauge invariance or diffeomorphism symmetry in that situation. It's exceptional when this equation is really well behaved in d+1 dimensions. And gravity isn't one of the exceptions, unfortunately, or fortunately. Maybe one day we'll learn it's fortunate. What I do find notable is that this equation is somewhat similar to the renormalization group equation of the worldsheet theory of the string. The renormalization group equation, if G is a coupling constant, is sort of dg dt. Sorry, I'm not set up to draw very easily here. But dg dt is minus dc dg. Where C is the Zama-logical of C function, which is very similar to the action. I wouldn't say it's fully understood, but you can easily believe that the Zama-logical of C function that appears here should be understood as the action in the classical limit of string theory. When I say the action, I mean the space-time action. So the only thing which is wrong, but it's fundamentally wrong, is that here G is complex conjugated on the right, and here it is not. And therefore, I have nothing useful to say.
I'm sorry, I did not understand. What is the problem with constructing symbols? Could you explain?
Well, formally, you can write down this equation. You can write down that equation formally for any theory. It's a partial differential equation in d+1 dimensions. If your gravity theory is in d dimensions, this is an equation in d+1 dimensions. You're only going to end up being happy if that's a nice equation, which is unusual. So it's a nice equation for Chern-Simons theory in 3 dimensions, for quantum mechanics in 1 dimension. And Gaiato showed that it's a nice equation for hypermultiplets in 2 dimensions. Or there's a situation related to a 3-dimensional hypermultiplet where it's a nice equation. It's a nice equation for current algebra in 2 dimensions related to hypermultiplets in 3 dimensions. In gravity, it's not a nice equation in any way I understand. I can't say more than that for sure.
What does nice mean?
Well, the ones I really know to be nice, they're elliptic differential equations. That only happens in the 3 cases I mentioned. And in those 3 cases, it leads to very special results. There's a different kind of niceness where the equation is parabolic.
I see. You're thinking towards constructing instantaneous solutions from such symbols, like going further to non-perturbative corrections. Is that the sort of notion of nice?
Well, okay. I just want to have a good theory of counting, being able to count solutions in principle. And if you just take a generic action, this is not going to be a well-defined, well-behaved equation mathematically. For example, in the case of gravity, it's neither elliptic nor parabolic nor anything. It's somewhat similar to the Ricci flow equation, except that you have to complexify the metric. So you could look at what mathematicians have done with the Ricci flow equation, where Perlman improved it to a version that was more respectable mathematically. If you could get what Perlman had for complexified metrics, maybe that would be useful. I'm not 100% sure you can't. I think what I wanted, which was to make contact with the RG equation, doesn't appear to work. for the stupid reason that G is complex conjugated on the right-hand side in one equation and not the other. Any other questions?
That's a good question. Will it be nice for the relativistic particle?
Well, a relativistic particle is quantum mechanics.
Right.
So it's nice in the sense that it's a mathematically there's some tricks involved. So first you have to complexify the field variables. So you have a quantum mechanics system with a phase space M. The question kind of leads to one of my favorite subjects. I've worked on it both recently with Davide Coyotto and also 12 years ago with Sergei Gukov. And it's also closely related to my papers on Covenant homology, geometric Langlands, and bunches of other things. So you have a phase space M, and complexifying the field variables means, so for gravity, we took the metric to be complex. We complexified the field variables. In quantum mechanics, it means that you have to complexify the phase space. So there has to be a nice complexification of the classical phase space. Otherwise, even to write a bad equation, you have to say what you're talking about, you have to complexify the phase space. Now, for a completely generic classical phase space, there's no nice complexification. But when there is a nice complexification, and it's a little bit elaborate to explain what makes a complexification nice, but when there is a nice complexification, then there are very nice results that result from it. In my opinion, a better framework for understanding quantization than the standard one. But that's a long story. And it's a very special taste. The kind of questions it answers aren't questions most physicists will ask about quantum mechanics. But yes, particle mechanics is potentially one of the three nice cases that I know of. The three cases that are nice in the sense that the flow equation is elliptic.
I guess I was more interested on the E part of the relativistic particle, like that E field that appears in the x dot squared divided by 2E. Will that E be complexified and that E playing the role of the metric on the world line?
Well, certainly in the spirit of this discussion, we should complexify E. I'd better not give you a quick answer. I've looked at this for quantum mechanics without a constraint. You're imposing a constraint. My guess is you could say something, but I don't know what would happen.
Is there anything that string theory tells you about how plausible this is, other than it's not obviously consistent, in other words, we can define branes and so forth? Is it like string field theory? Are there any hints that this is the right way to go?
I don't know any hint from string field theory. I didn't explain this in detail, but Lukin and Sorkin, okay. If you want to do string perturbation theory in Lorentz signature, first of all, Lukin and Sorkin essentially explain how to do it. So you can use a Lorentz signature metric except at the interaction points, but you need to regularize the situation slightly near the interaction points. And Lukin and Sorkin showed something nice. So just to make the metric non-degenerate, you could give it, you need an I epsilon with either sign. But one sign gives an allowable metric, the other doesn't. And one sign gives a positive, the action you have to remember is minus R times root G in Euclidean signature. So the action for a sphere is negative, but the action for a Riemann surface of homogeneous is positive. We want to get a positive action here, but we're in Lorentz signature except at the branching point. Luko and Sorkin showed that if you pick the sign of the regulator so that the metric is allowable, then the action gets a positive real part. But in Lorentz signature, there was an I. I've missed, okay, sorry. I didn't give a completely coherent explanation, which takes a little bit longer. But the metric was in Lorentz signature away from this point, so the action was imaginary except at that point. And then you'd like to make sure that the contribution you get near that point is a positive contribution to the action. So Luco and Sorkin showed that that's true if the sign is such that a scalar field would have made sense. So in the language I'm using now, that's true for allowable metrics. It's not true for completely general invertible complex metrics. You could have picked a regulator of the wrong sign. Then the scalar quantum corrections to the scalar field don't make sense, and the action has the opposite sign from what you wanted. So I think that shows pretty convincingly that if you want to do string perturbation theory with physical strings in real Minkowski space and real world sheets, this is the way you need to regularize the interactions. That doesn't answer your question about, doesn't quite answer your question about string field theory. This is for the simplest cubic interaction vertices, one string breaking into two. String field theory, Zwiebak has more complicated vertices, which I didn't try to think about in this context. My guess is they would all work.
It's very exciting. Thank you. If one were to go back to 3D gravity, there were puzzles there about which saddle points to and not to include. Does this clarify them now?
You don't get anything for free out of this. It'll tell you not to include, well, no one in practice has tried to include unallowable ones. Anything anybody's tried to include was, after all, people try to use real saddle points. Those are all going to be allowable. If there isn't quite a real saddle point, to get as close to that as they can. So for example, okay, this didn't work in Lorentz signature, but Luco and Sorkin just fixed it, just barely. Okay. The things anything anyone has used in practice where they got a sensible result, I think was allowable. That might not be strictly true, but okay. The things I've looked at weren't counterexamples, but maybe I've overlooked something. I looked at a few cases that I didn't discuss in the lecture, including time folds, the double cone of Dodge, Schenker, and Stanford. Yeah, okay. Those are the main examples I didn't discuss in the lecture that I have looked at. Any more questions?
If not, shall we thank Edward again? Thank you for joining us. And
thank you for the invitation. Okay, bye-bye, everyone. Be well, stay safe.
bye-bye.
Thank you. Bye.